All right, silly people, here's the situation. We're going to be doing a wave function, um, which is a addition of two wave functions, the ground state and the first excited state, psi1 and psi2. Um, and we're going to normalize it. We're going to find the expectation value of position, that of momentum, um, and also discuss some energy values for it. So to normalize it, um, you're you're going to take the integral over all space of the square modulus of this thing. Um, and before actually plugging in the definitions of psi 1 and psi 2, I'm going to expand this thing. Um, it'll be a squared, first of all, so there's going to be an a squared out here. 0 to a, we're going to have a psi 1 star x, psi 1 of x, uh, plus psi 2 star of x, psi 2 of x, plus psi 1 star, psi 2 plus psi 2 star psi 1. And we can rewrite at least the first two of those as being a squared times the integral from 0 to a of the square modulus of psi 1 plus the square modulus of psi 2, right? But then these two guys over here are interesting. We actually have the integral from 0 to a, or a squared times the integral from 0 to a of psi 1 star psi 2 dx plus a squared 0 to a psi 1 star psi 2, and that's actually 2, 1 is that pair there. 2, 1 dx. And both of those are invocations of the orthogonality condition for wave functions in this system. That is, that the integral of psi n star psi m dx is actually equal to a Kronecker delta, delta mn, where it's equal to, it's equal to 0 if m is not equal to n, and 1 if m is equal to n, right? So going back to our integral, we can rewrite the terms on the end there as being a squared Kronecker delta 1, 2 plus a squared Kronecker delta 2, 1. And all of it has to be equal to 1. Since 1 is not equal to 2, these are both gone. So what we're actually calculating is just the sum of the two square moduli, maybe, of the first two wave functions. Now, the wave function in position space for state n, psi n of x, is equal to the square root of 2 over a times sine n pi x over a. These are the solutions for the particle in a box. So just using that, we are going to get some forms for these. So I'm going to move a squared to the other side, actually. So it's going to be 1 over a squared over here. And then we're going to have the integral from 0 to a, you have 2 over a out here because we're squaring it, and this is going to be sine squared 1 pi x over a, so just pi x over a dx, and then this is going to be also 2 over a, but now it's the integral from 0 to a of sine squared 2 pi x over a, right? And so, I mean, I'm going to use a trig identity here, and I'm actually going to use it several times during this. So it's going to be that sine squared theta is equal to 1 minus cosine 2 theta over 2. So using that trig identity removes the factor of 2 that we had before, and this becomes 1 over a, and then this is going to be the integral of dx minus the integral of cosine 2 pi x over a dx evaluated from 0 to a, and this is going to be 1 over a integral of dx minus integral of cosine 4 pi x over a dx. All of that is equal to 1 over capital A squared. Those integrals aren't too bad to do now, so this is x squared. No, it's not x squared, it's just x. And this is a over 2 pi sine 2 pi x over a. And then we got x again, and we have a over 4 pi sine 4 pi x over a from 0 to a equals 1 over capital A squared. And then evaluating at the bounds, we have a, we got minus a 2 pi sine 2 pi, and then 0, and then the sine of 0, which is 0, so that's done. And this is 1 over a minus a over 4 pi sine 4 pi minus 0 plus sine of 0, so again 0. So it's 1 over a squared. Sine of 2 pi and sine of 4 pi are both 0 as well, just because they're both full rotations. So those are gone as well. And so we ended up with 2 over a. No, not even 2 over a. We have 2 over a times a, which is 2, which is equal to 1 over capital A squared. So we find that a is 1 over root 2. That properly normalizes our combined wave function. I'll write it again. Capital psi x and 0 is 1 over root 2. We had psi 1 of x plus psi 2 of x. Then it asks us to find what the time dependent form of this actually is, which we're going to need for the next bit. So not a silly step by any means. Expanding the definitions of, or actually not even expanding the definitions. I'm going to rewrite the definition of the wave function again, but this time for time dependence being involved. Again, it's root 2 over a times sine n pi x over a. And then I had the formula right here, I swear. It involves an exponent minus I n squared pi squared h bar over 2ma squared with t up here. That's how to get the time dependence in. And so how we're going to do this is we're going to expand psi 1 of x into psi 1 of x into t, do the same for psi 2 of x, and try and simplify that form. So we have that psi of x and t is now 1 over root 2. We got root 2 over a sine pi x over a exp. We got minus 1 squared is 1, so it's just I pi squared h bar t over 2ma squared, and then plus root 2 over a sine of 4 pi x over a. No, not even 4 pi x, it's just 2 pi x. But then this is going to be e to the, now I'm running out of room. I'm going to just move this John down here. We got minus 4 over 2, which is just 2. So minus I times 2 pi squared h bar t over ma squared. Right? Whoops, I'm scaling too far. That's all cool, but we can simplify it even more. So factoring out the root 2, those will cancel out with the normalization factor, but also factoring out a root 1 over a. We'll write the simplest form that we can get for just the complete wave function. That h bar is not squared, I don't think. 2ma squared plus sine 2 pi x over a exp minus I 2 pi squared h t over ma squared, right there. And actually, we can write it with this omega factor, which Griffiths defines as h bar pi squared over 2ma squared, since they both kind of share that value. So we can write this as 1 over root a sine pi x over a e to the minus I omega t plus sine 2 pi x over a e to the minus 4I omega t. And we'll leave it like that. And so the next part of the problem is to get the square modulus of this, which is pretty awesome. The square modulus is defined as multiplying the complex conjugate of it by the non-complex conjugate version of it. So we're going to end up with a factor of 1 over a out front. And then now just writing all this out, sine pi x over a e to the I omega t plus sine 2 pi x over a e to the minus, or just positive 4 I omega t times sine pi x over a e to the minus I omega t plus sine 2 pi x over a e to the minus 4I omega t. Just expanding those combinations, we'll end up with sine squared pi x over a. We'll end up with sine squared 2 pi x over a. And then we'll have plus sine pi x over a times sine 2 pi x over a, all times this weird factor of e to the minus 3I omega t plus e to the 3I omega t. Right? And we can write this in a way that is a little bit more suggestive. I realize that my parentheses are now getting a little bit bonkers. We got sine squared 2 pi x over a. We got sine, I'm going to pull out a factor of 2, actually. So 2 sine pi x over a, sine 2 pi x over a. And then we have e to the minus 3I omega t plus e to the 3I omega t over 2. And if you haven't seen this before, cosine of z is equal to e to the iz plus e to the minus iz over 2. So instead of having exponentials, we just have a cosine, actually. So finally, the square modulus can be written as 1 over a sine squared pi x over a plus sine squared 2 pi x over a plus 2 times, or 2 sine pi x over a sine 2 pi x over a cosine 3 omega t. Right. That was a lot of work for a cosine, but hey, what can you do? Then the problem asks us to do something with that there square modulus and calculate a expectation value for position, which will be given by the integral from 0 to a of the square modulus times x dx. And so it's going to be 1 over a, and we'll have I'm going to introduce some big brackets, from 0 to a of x sine squared pi x over a dx plus 0 to a x sine squared 2 pi x over a plus, and that's a dx, plus 2 cosine 3 omega t integral from 0 to a of sine pi x over a sine 2 pi x over a dx. Now I'm going to do a trig identity to simplify these integrals. In blue, we're going to say that cosine, or actually, we've already done that one. Sine squared is equal to 1 minus 2 cosine over 2. But also, sine x sine y equals 1 half cosine x minus y minus cosine x plus y. We're going to use that to simplify the third integral there. So applying all of our trig identities, we have that this is 1 over a, then we got 1 half integral, or actually, this is going to get kind of big. Let's factor out a 1 over 2a in total, because we're going to have an integral of x dx minus an integral cosine, no, it's actually x cosine pi x over a dx plus just simplifying the other integral of x dx, minus the integral x cosine. This is a 2 here. This is actually a 4 here over a dx. That does it for that. And then we have also a 2. Actually, there's no factor of 2 anymore because there is a factor of 2 right there. So just cosine 3 omega t over a times this stuff in here. This is evaluated from 0 to a. We got the integral of, there's supposed to be an x here. Yeah, so it's x, and then pi minus 2 pi is minus pi, so it's the cosine of minus pi x over a dx, plus, or minus, we got x cosine, and then pi minus 3 pi is 3, so 3 pi x over a dx. Okay, and that's all from 0 to a. It's a lot of funky little integrals. And all 4 of these cosine integrals have to be evaluated independently via integration by parts. So let's come up with a system of integration by parts where we do u equal to x, du will be dx. We have all these cosine terms for dv, so cosine n pi x over a dx, and then the integral of that is a over n pi sine n pi x over a. And you already saw this in the part where we calculated the normalization constant. Whenever we evaluate something that has a sine function, from 0 to a of this combination of stuff goes to 0 for both of the bounds. So I'm going to say that any contributor from uv evaluated from 0 to a is going to equal to 0. But we're still going to have this integral of v du for each one that we'll have to calculate. So just neglecting the uv part of integration by parts, we have that our integral is 1 over 2a. The integral of x is x squared over 2. We have actually plus v du, so a over 2 pi times the integral of sine 2 pi x over a. We have another x squared over 2. We have another plus, but it's a over 4 pi now, times the integral of sine 4 pi x over a dx. There's supposed to be a dx there. All from 0 to a. We also got this plus cosine 3 omega t over a. But in here, again, we're ignoring the uv stuff, so this is going to be minus just a over pi. Let me make a note here that cosine of minus theta is equal to cosine of theta. And so I'm just treating pi x over a the same as negative pi x over a for reasons of minus sign cohesion. So we have minus a over pi integral of sine pi x over a dx, and then this is going to be minus the integral minus a over 3 pi, the integral of sine 3 pi x over a dx, evaluated from 0 to a. Let's start. Well, actually, let's not evaluate yet. Let's actually do those integrals that are in there. Adding together the x squared stuff, we got x squared here. That's going to be a over 2 pi squared. You actually get a minus cosine 2 pi x over a. And you get a minus a over 4 pi squared cosine 4 pi x over a from 0 to a. And then we also have plus cosine 3 omega t over a. We got actually just a squared over pi squared plus a squared over pi squared. Nah, this is supposed to be positive. So minus a squared over 9 squared pi squared. My 9's look identical to my a's. I'll try not to make that problem again. But then both of these are multiplied by sine functions actually. So cosine pi x over a minus a over 9 pi, a over 3 pi squared times sine, nope, cosine. Cosine of 3 pi x over a. We're getting there. Now we can evaluate at the endpoints. So we got 1 over 2a, we got a squared, we got minus a squared over 4 pi squared. Cosine of 2 pi is 1, so that looks good. We got a squared over 16 pi squared. Cosine of 4 pi is 1. We got 0, and then we got plus a squared over 4 pi squared. Cosine of 0 is 1. And then we got plus a squared over 16 pi squared. And then cosine of 0 is 1. So that's it for the first term. And then we have the funky time-dependent term where we're going to have a squared over pi squared. Cosine of pi is actually minus 1, so we're going to have minus a squared over pi squared. Then we're going to have the cosine of 3 pi is actually minus 1, so we're going to add a squared over 9 pi squared. And then cosine of 0 is 1, so we're going to have another minus a squared over pi squared, and then cosine of 0 is 1, so we're going to have another a squared over 9 pi squared. Alright, so we can cross this thing out with this thing, and also this thing out with this thing. But the other stuff actually add up. So we have 1 over 2a times a squared plus cosine 3 omega t over a. Then we have minus 2a squared over pi squared plus 2a squared over 9 pi squared. Simplifying, we got a over 2 there, and cosine 3 omega t over a, we're going to factor out 2a squared over pi squared. Oops, it's just a on the bottom. 2a squared over pi squared times minus 1 plus a ninth. So we got a over 2. We got actually now 2a cosine 3 omega t over pi squared. And then 1 minus 1 ninth is 8 ninths. So let's make this into a minus 8 ninths. Nice. Simplifying further, we got a over 2 minus 16a cosine 3 omega t over pi squared. We can simplify an additional factor of a over 2 from both of these. So we have a over 2 times 1 minus 32a cosine 3 omega t. There's a 9 on the bottom here that I was neglecting. Over 9 pi squared. I'm just making sure that that matches my notes. Yeah, cool. So that's your expectation value of x. It's where you expect the particle to be just by looking at it. And actually, there's not an a here, so cool. Now, it does ask you to think about the amplitude of the wave that is produced by the expectation value, because it is a wave. It's oscillating cosinusoidally. It's kind of going like, I don't know, like this. And it's going to have some amplitude and it's going to have some frequency. The frequency isn't hard to think about because the frequency is built into the cosine function. The angular frequency is just 3 omega. Not too crazy there. The amplitude then is going to be the entire coefficient that is attached to the cosine function. So we find that the amplitude is a over 2 times 32 over 9 pi squared. And we'll leave it like that. And then it also asks you to calculate the expectation value of momentum. Just use Iron-Fest's theorem for this. I think Griffiths says, what does he say? He says something silly in some silly voice. Do it the quick way, Johnny. Yeah, so Iron-Fest's theorem is the quick way. And so let's just multiply our result for the expectation value of x and take a derivative with respect to time. So we have ma over 2 times 32 over 9 pi squared times the time derivative of cosine 3 omega t with a minus sign on it, which will actually give us a ma over ma times 16 over 9 pi squared 3 omega sine omega t. Be careful, silly people. I wrote a sine omega t instead of a sine 3 omega t. There should be a 3 in there, and I do that a bunch of times, so be wary of that. Which simplifies to ma 16 ma omega sine omega t over 3 pi squared, and then you can put in back the definition of omega that old Griffiths provided, which was pi squared h bar over 2ma squared. Putting that in here, we have 16 ma sine omega t 3 pi squared pi squared h bar over 2ma squared. This will reduce to 8. The m's are gone. I'm going to put the h bar up top. We still have the sine function. But now this is just over 3a. Okay. 3a. Awesome. That's our momentum. And the problem also asks what are the possible values for the energy when you actually measure this. It's going to be E1 and E2, right? Those are the possible ones because it's a wave function which is just a combination of the first two energy eigenstates. If it was a sum over all of the energy eigenstates, like an actual particle in a box, then you can have any energy. But since it's just the first two, we just have the first two. And since we normalized it so that they're just pretty much adding together with the same multiplier, then we know that the probability of each of them is going to be 1/2. There's probably a more rigorous way to calculate that, but that's just how we define the problem. They're both a half. Also, you can calculate the expectation value of energy, which will just be the average of the two possible energies. So it's going to be 1/2 of, using the definition of the energies for the particle in the box, we've got pi squared h bar squared over 2ma squared, that's E1, and then E2 is 2 pi squared h bar squared over ma squared. And so we got, just adding these together quickly, 5 pi squared h bar squared over 2ma squared. So we have 5 pi squared h bar squared over 4ma squared. Okay. I think that looks good to me.